Good evening, I'm Grant Canese for Team 26, and tonight we're going to solve a hydraulics problem for you. As you can see here for problem 2, we have a channel with section 1 to 2, uniform flow, 2 to 3, a bump, and 3 to 4, a hydraulic jump. The ultimate goal in the problem is to figure out the height in the stagnation tube at point 4. 2A says our procedure with the steps involved in solving the problem. We'll start with section 1, or Roman numeral 1, section 1 to 2. We know it's uniform flow, so we can use Manny's equation to figure out V and then Q from that. And we also know on uniform flow that energy at point 1 is equal to energy at point 2. Manny's equation gives us V from and slope. All the values we need are given in the problem statement. We just plug them in and go. K is 1.0. N is 0.011. Awesome. Is A over P. Over 2 times 0.05 meters plus 3 meters. And slope is 0.1. This gives us a V of 3.82 meters per second. We know Q is equal to V times A, and therefore 3.82 times 0.05 times 3, which is our area, is equal to 0.573 meters cubed per second. From our flow rate, we can determine our lower Q, which is Q over base, is equal to 0.573 again over 3, which we get as 0.155 meters squared per second. From this Q, we determine our critical depth, given as the cube root of Q squared over G. I'm sorry, I wrote this down wrong. This Q is 0.191. We'll plug that in over gravity and gives us YC as 0.155. From there we can get our Freud number, which is equal to YC over Y to the 3/2. Sorry, 2/3.
Great, it's 3 halves.
Yeah, it's 3/2. I contradicted myself. Our Freud number is 5.45, and we know any Freud number over 1 is supercritical, which is our answer to 2B. Continuing on, since we know points 1 and 2 are equal, the depth at 1 is equal to depth at 2. The V and Q at 1 are both equal to the V and Q at 2. We can then go to the section Roman numeral 2 we have here is solving for a bump, in which we'll take the energy balance equation. E2 is equal to E1 minus delta Z. Energy is equal to F13Y3 plus Q squared over the quantity 2 by squared G. Same for point 2, y2 plus q squared over 2 by2 squared G, and of course minus our delta Z. Plugging in our numbers, we get y3 and then minus our delta Z, which is given in the problem as 0.3. Using a TI-89 graphing calculator or online solver, we solve for y3 is equal to 0.0662 meters. From there, we can move on to solving for y at 4. And we'll use a derivation of a momentum equation and Froude number as y4 is equal to y3 over 2 times -1 plus the square root 1 plus 8 times our Freud number of 3 squared. So computing Freud number for 3, we use the same equation as previous. YC over Y3 with 3 halves. Our YC again is 0.155. Our Y3 we just figured out was 0.0662. And that gives us a Freud number at 3 of 3.58. Plugging everything we know into this equation, we get 0.0662 divided by 2 times -1 plus square root of 1 plus 8 times 3.58 squared. At y4, we have 0.304 meters. Now that we have y4, we can go to our final section, the bump. We'll use a simple equation, h is equal to v squared over 2g. To find v4, we know q1 is equal to q4 is equal to v4 times a4. We rearrange that to get v4 is equal to q, 1, 4, 2, whatever, over a4. So we have 0.573 over y4, 0.304 times our base of the channel, which is 3. This gives us 0.625 meters per second at 4. We plug this into our H equation. We get 0.625 squared over 2 times 9.81. And we get a height of 0.0199 centimeters, or meters, or 1.99 centimeters. For our final section of the problem, we'll do the energy curve with Tyler.
Hi, this is Tyler from Team 26, and I'll be showing you how to do part 2D. First, we are going to take the Y values, the depth values that Grant found earlier, and we're just going to plug them into this chart. From there, we're going to solve for the area of each cross-section. So we will multiply each y by the width of 3 to get, so for section 1, we'll get 0.15 meters squared. For section 2, we'll also get 0.15 meters squared. For the third section, we'll get 0.186 meters squared. For the fourth section, we will get 0.912 meters squared. And for the critical section, we'll get 0.465 meters squared. From there, we're going to plug in to the equation to solve for E so that we can graph it. So as we know, E equals the depth plus flow rate squared divided by 2 times gravity times area squared. So I'll do one sample calculation, and then you can do the next 4 on your own, and I'll just solve for the values. So for number 1, we're going to take the y of 0.5, add that to the q, which remains constant for the entire problem. Divide that by 2 times gravity, 9.81, times the area for that cross section, which is 0.15. Square that. So you have your values like this. When we solve for that, you will get an E of about 0.793. So you'll go ahead and plug that into your chart, and you'll do that 4 more times. I'm just going to go right in the values right now. Both 1 and 2 are going to be 0.71793. For 3, you are going to get 0.490. For 4, you'll get 0.324. And for critical, you'll get 0.232. Now, you're going to plot your y values against your e values on the chart. And don't forget to convert them into centimeters, so multiply everything by 100. So our first point is going to be at 0.05 for y and 0.79 for e, which is going to be right out about here for 0.1. 0.2 is also at the same y and e, so we're going to plug that one in right here also. The third point is at 0.066 and 0.49. So we will also put that one on the graph. Next is the 4 value. So that is at about 30 centimeters and 32 centimeters for E. So that value is up here. And your critical value will be at about 15 centimeters for Y and 23 centimeters for E. So that's going to be right about here. So to create the specific energy line, you're going to connect those. And There's the answer to number 4, or number D.